Have you ever wondered what happens when a star dies? Or where the universe ends? Well, welcome to the captivating world of black holes, the most mystifying entities in the cosmos. These cosmic conundrums are regions in space where gravity is so strong that nothing, not even light, can escape their gravitational pull. They are born from the remnants of massive stars that explode as supernovas. After such an explosion, what's left collapses under its own gravity, creating a single point of infinite density known as a singularity. This is the heart of a black hole. The discovery of these cosmic entities has revolutionized our understanding of the universe, making them an intriguing subject of study. Their existence challenges our perceptions of space and time, leaving us with questions that boggle even the brightest minds. Black holes, the universe's ultimate enigma, are about to reveal their mysteries. Imagine a star, millions of times the size of our sun, collapsing under its own gravity. This is where our journey into the formation of black holes begins. To understand the birth of a black hole, we need to take a quick detour into the life of a star. Stars, much like our own sun, are gigantic nuclear furnaces, fusing hydrogen into helium in their cores. This process releases a colossal amount of energy, which pushes against the star's gravity, maintaining a delicate balance. However, this balance cannot last forever. Once a star exhausts its nuclear fuel, gravity takes the upper hand, causing the star to collapse. Now, if the star is massive enough, this collapse triggers a supernova explosion, an event so bright it can briefly outshine an entire galaxy. But what happens next is even more fascinating. The core of the star continues to shrink under the relentless pull of gravity, condensing into a point of infinite density known as a singularity. This singularity, hidden by a boundary called the event horizon, marks the birth of a black hole. But stars aren't the only cosmic nurseries of black holes. Sometimes when two smaller black holes orbit each other, they can spiral inward and merge to form a larger black hole. This violent cosmic dance sends ripples through the fabric of space-time, known as gravitational waves. It's important to note that not all stars end up as black holes. Only stars with a mass about 3 times that of our sun or larger can create a black hole. For less massive stars, their fate lies in becoming a neutron star or a white dwarf. That said, the exact conditions and processes that lead to the formation of black holes are still a topic of ongoing research. Scientists continue to delve deeper into the mysteries of these enigmatic cosmic entities, unlocking new insights and challenging our understanding of the universe. The birth of a black hole, an event of cosmic proportions, is nothing short of spectacular. And as we delve deeper into this topic, you'll discover just how truly intriguing these celestial phenomena are. A black hole is not just a point in space, it has structure, parts, and a boundary from which nothing escapes. Now let's take a closer look at the anatomy of a black hole. The first part we encounter on this journey is the event horizon. This is the boundary that marks the point of no return. Once anything, even light, crosses this threshold, it cannot escape the gravitational pull of the black hole. The event horizon is not a physical structure, but rather an invisible line in space, marking the black hole's outer boundary. Next, we delve deeper into the black hole beyond the event horizon where we find the ergosphere. This region is a bit peculiar. It's an oblate spheroid shape stretched out at the equator due to the black hole's rotation. In the ergosphere, space and time behave quite strangely. While you can't escape the black hole entirely, you can still escape from the ergosphere and return to the universe outside. But what's at the very heart of a black hole? This takes us to the singularity. A singularity is a point of infinite density where all the mass of a black hole is concentrated. It's the core that gives a black hole its incredible gravitational pull. The laws of physics as we understand them break down here. In fact, our comprehension of space and time cannot fully grasp what a singularity is. There's another intriguing feature about black holes, their rotation. Some black holes spin, and this rotation can create a ring singularity and an inner event horizon, adding another layer to their complex structure. Remember, black holes aren't empty voids. They're dense, dynamic, and incredibly complex. The more we learn about them, the more intriguing they become. They challenge our understanding of the universe, pushing the boundaries of what we know about space, time, and the laws of physics. A black hole, more than just an abyss, is a complex and fascinating structure. So, next time you gaze up at the stars, spare a thought for the cosmic wonders hiding in the darkness, the mysterious and powerful black holes. Black holes exert a gravitational pull so strong that not even light can escape. But why is that? Let's dive into this fascinating world of cosmic giants to find the answer. To understand why nothing can escape a black hole, we first need to grasp the concept of escape velocity. Picture this. You're tossing a ball into the air. The ball ascends, slows down, then falls back to Earth. But what if you could throw the ball so hard that it never comes back? That's essentially what escape velocity is, the speed needed to break free from a celestial body's gravitational pull. In the case of Earth, this speed is around 25,000 miles per hour. For less massive bodies like our moon, the escape velocity is lower. Now, imagine a body so massive and dense that the escape velocity exceeds the speed of light. That's right, we're talking about black holes. Now, the speed of light is a cosmic speed limit. Nothing in our known universe can travel faster. So if the escape velocity of a black hole exceeds this limit, it means nothing, not even light, can escape its gravitational pull once it gets too close. But how close is too close? This brings us to the event horizon. The event horizon is essentially the boundary around a black hole beyond which nothing can escape. It's the point of no return. Once something crosses the event horizon, it's destined to fall into the black hole, never to emerge again. It's like a cosmic one-way street leading to an unknown destination. This is why black holes are black. Their gravitational pull is so strong that it traps light beyond the event horizon, rendering the black hole invisible to conventional observation methods. The event horizon marks the point of no return, a boundary drawn by the relentless grip of gravity. This invisible boundary and the concept of escape velocity are key to understanding the enigmatic nature of black holes, painting a picture of a cosmic phenomenon that continues to fascinate scientists and laymen alike. Near a black hole, time slows and matter stretches. Strange things happen when gravity is off the charts. Let's venture into the mind-bending universe of black holes where the usual rules of physics take a back seat. First, let's talk about time dilation. Now, what's that? Well, it's the idea that time doesn't tick at the same rate everywhere in the universe. Near a black hole, the gravity is so strong that time actually slows down. If you were to watch a clock falling into a black hole from a safe distance, you would see it ticking slower and slower until it seems to stop entirely at the event horizon, the black hole's point of no return. This is not some science fiction trope, but a real consequence of Einstein's theory of relativity. Now let's move on to something even more bizarre: spaghettification. This odd-sounding term describes what would happen to an object, or heaven forbid, a person who gets too close to a black hole. The gravity at your feet would be much stronger than at your head, stretching you out like a piece of spaghetti. This extreme tidal force can stretch and compress objects into long, thin shapes, hence the term spaghettification. But don't worry, you'd have to get pretty close to a black hole for this to happen. And by that point, you'd have other things to worry about, like the fact that escape becomes impossible beyond the event horizon. So, what have we learned? Black holes are not just points in space swallowing everything in their path. They are fascinating cosmic entities where time slows and matter stretches. They are laboratories of extreme physics, enabling us to test our understanding of the universe in ways we can't on Earth. In the vicinity of a black hole, time and space behave in ways that defy our everyday intuition. But that's what makes black holes so incredibly captivating, isn't it? Black holes are not eternal, they glow, they evaporate. But how does that happen? Let's dive into the cosmic conundrum of Hawking radiation and black hole evaporation. Imagine a black hole. It's a cosmic beast, a place where gravity is so intense that even light cannot escape its grasp. Yet, within the inky darkness, something fascinating occurs. It's a phenomenon known as Hawking radiation, named after the brilliant physicist Stephen Hawking. In the 70s, Hawking proposed a theory that defied the conventional understanding of black holes as eternal, unchanging entities. According to quantum mechanics, the vacuum of space is not truly empty. It's teeming with virtual particles, pairs of matter and antimatter that pop into existence and annihilate each other in an instant. But near the event horizon of a black hole, something different happens. If one particle falls into the black hole while the other escapes, it transforms from a virtual particle to a real one. This escaping particle is what we call Hawking radiation. But here's the kicker. The energy to transform the escaping particle from virtual to real has to come from somewhere. And in this case, it's borrowed from the black hole itself. This process, repeated over and over again, leads to the black hole slowly losing mass, or in other words, evaporating. However, don't expect to see a black hole vanish in a puff of smoke anytime soon. The evaporation process takes an incredibly long time, longer than the current age of the universe for most black holes. But theoretically, at the end of this process, the black hole could eventually disappear completely, leaving behind only a faint whisper of Hawking radiation. So, even black holes, the universe's ultimate hoarders, cannot escape the laws of quantum physics. They glow with the energy of escaping particles. They slowly evaporate over eons, and perhaps they even meet their end in a final spectacular burst of energy. Black holes, the universe's ultimate mystery, continue to challenge our understanding of the cosmos. As we delve deeper into the fabric of space-time, the enigmatic nature of these astronomical phenomena keeps us on our toes, pushing the boundaries of our knowledge and igniting our curiosity. Let's take a moment to recap what we've learned so far. We've explored the formation and anatomy of black holes, from the collapse of massive stars to the singularity at their core. We've examined the concept of escape velocity, the point of no return at the event horizon, and the mind-bending effects of time dilation and spaghettification. We've also contemplated the intriguing notion of Hawking radiation and the theoretical evaporation of black holes. Yet, despite these discoveries, there's still so much we don't know. For instance, the information paradox remains one of the biggest unsolved mysteries in physics. It questions what happens to information about matter that falls into a black hole. Does it disappear forever, contradicting quantum mechanics, or is it somehow preserved? These are questions that researchers around the globe are grappling with. Then there are the exotic types of black holes, like rotating and charged ones that we've only just begun to understand. There's also the tantalizing prospect of black hole mergers and the resulting gravitational waves, a relatively new field of study that promises to shed light on the darkest corners of the universe. As we continue our journey, it's important to remember that our understanding of black holes is still evolving. With every new observation, every novel theory, we inch closer to unraveling their mysteries. But the road is long and filled with unknowns. So what's next in our quest to understand black holes? Only time will tell. As we continue to explore these cosmic enigmas, who knows what other secrets they might reveal. Until then, the mystery of black holes continues.